Okay, so here we are at the last of our videos on metals. So this video is going to talk about how we modify metals. So as you know, we use metals all over everywhere in our society for structural reasons, for wiring, for all different types of applications. And a lot of the time we need to modify them in order to make them suitable for those applications. And we're going to look at those today. So very few metals are used in their pure form, okay, so as they're dug out of the earth. So I want you to have a think about two that you can think around the home that might be used without modification. Do we use them as pure substances? Make a note of those and we'll talk about it when we're in class. Okay, so generally, most of the metals we use in society are used as alloys, which means a mixture of different metals. Sometimes non-metals, but for the most part, when we talk about alloys, we're talking about a mixture of metals. And they combine these metals to allow for us to select specific properties that we're after. They can be modified by heat treatment, so different ways that we can heat and cool them in order to have specific properties, and by applying coatings to them, such as paint. So this diagram here shows a number of different metals, and you don't need to know about all of them. You should know a couple of examples of specific alloys that are used, however. So you may want to know if there are alloy between a metal and a non-metal, like something like steel perhaps, or if there are different combinations of metals to make the alloy, like the nickel alloys that we use for our coins. Okay, so essentially we define alloys as solid solutions, okay? They usually contain more than one metal, but because they are all metals for some of them, it's still metallic bonding. And in the case of steel, where we've got small amounts of carbon in there, it's actually still considered metallic bonding as well. And we'll see that when we talk about that type of alloy a bit more later. Okay. So these are some of the examples that we have. So amalgam, if you know anyone with old dental fillings, amalgam was used in old dental fillings. Brass, like your brass keys, is also an alloy. Solder for doing electrical boards and things like that. Steel, sterling silver, and even white gold. So alloying is done in a number of ways, okay? So essentially what we need to do is be able to mix the metal with another metal, which means they need to be in the liquid state because it's very hard for us to sort of mix solids and them to join together. So when we make an alloy, we melt the metals down. Sometimes non-metallic atoms can be added in, such as carbon and silicon, okay? And they'll be used to form a particular type of alloy. We melt the metals down, and then when they harden again, okay, so when they solidify, what we find is that they are generally harder, they're less malleable, and they don't conduct as well as the individual metals did on their own. Okay, and this diagram over here shows you what happens to the metallic lattice as a result. Okay, so in a pure metal, when we apply a force, remember it will bend without too much problems with our malleability. Okay, so we'll get distortion through here where the cations just roll over each other. But in an alloy, because the other metal that we've put in is a different size, okay, we've got size differences, that lattice no longer behaves in quite the same way. As the other cations move across, they hit something that's a bit bigger, so they don't roll over it as well. So we get these pockets where the lattice isn't quite as uniform as we might think, and that can stop it from rolling properly. So this is where we get the hardness from. Okay. So there's two main types of alloys that we need to know. Substitutional alloys, and if you think about the word substitute, that's exactly what it means. We're substituting out cations in the normal lattice for cations of a different metal. In this case, they are usually a similar size. Okay, so you can see here these yellow cations here are a similar size, not quite the same as the cations in the main lattice. Whereas interstitial alloys, you can see here that the particles that are in here in yellow, which is what we're making the alloy with, are much smaller. Okay, so instead of slotting into the lattice, they slot into the gaps between the lattice cations. Okay, so let's look at these in detail. Substitutional alloys, the atoms of the metals being used to form the alloy are about the same size. Okay, not exactly the same size, but roughly the same size, so silver and copper. Okay, they take the position in the lattice. So as we saw in the previous diagram, if we have our lattice, the new ones, okay, the substituted ones, take the position in the lattice, okay? So they're actually within the metallic lattice itself, okay? And they sit in the array even though they may not fit perfectly. Okay, so sterling silver and brass are both examples of substitutional alloys. Sterling silver has a mixture of silver and actually some copper, and by adding the copper we actually make it shinier than normal silver and give it a bit of corrosion resistance, which is why a lot of jewelry is made out of sterling silver. The other alloy that you may be familiar with jewelry is, if you have a look, anyone who has some silver jewelry, the hallmark 925 actually indicates a nickel silver, so it's got a bit of nickel combined with the silver as well. Okay, so if we have a look here, just a few more diagrams, okay, and here we see some of our examples. So this is the composition of sterling silver, okay, so we take silver at about 92.5% and about 7.5% copper. We take ingots of these two metals and then we melt them down, mix them up, and when it resolidifies, we have a metallic lattice which is just over 90% silver and 7.5% copper. Okay, so the new metal is a combination of both of those. Brass, it has different combinations depending on the type of brass that we have, but it is a substitutional alloy that is made between copper and zinc. Okay. So remembering these are two quite good examples that you could use when explaining substitutional alloys. We don't need to know all of them, but we should have a couple of examples that we can draw on when answering questions. So substitutional alloying with for steel, okay, so we can take iron and alloy it with manganese or chromium or nickel and cobalt, and they get different properties and different uses as a result. Okay, so if we alloy it with something like cobalt, we actually get some pretty good magnetic properties. It improves the magnetic properties of the steel and it improves its resistance to temperatures. So we're using alloys and we design alloys in order to improve the properties that we want for a specific application. Okay, so in the case of manganese, we add in manganese and it increases strength and toughness, so it's good for things like bicycle frames where you want them to be quite thin but still have the strength to carry a whole person around and undergo some of those shocks if they're going over bumps and things like that. Interstitial alloys, okay, so remembering substitutional alloys, we swap one for the other, like substituting out a player during sport. But interstitial, we have this interstitial, which it means within the spaces. So in interstitial alloys, we're looking at a solution, a solid solution again, but this time we're kind of looking at the cations like a solvent. So these are our metal cations here, the green ones. Okay, and then what we're alloying with, our alloying substance, is like a solute. Okay, it's what's being dissolved in there. In this case, it's quite often carbon or silicon. There's a couple of others, but they're our most common ones. Okay, so this we get when we, again, melt them down. So we melt down the iron and then we add in some carbon. Okay, and instead of taking the position in the lattice, these are too small and they fall into the gaps between them. Okay, can you think of what would happen if in our lattice we now have things that are stuck within the gaps? Have a think about it. Okay, so when we do get these types of alloys, lost my information. There we go. When we do get these types of alloys, we see new properties dependent on the percentage of what we're adding in. Okay, so again, as we saw with the other ones, and we mentioned in general with alloys, this increases the hardness, okay, but anytime we increase hardness, we often increase brittleness as well, okay. So you think about that with your phone glass. People wanted harder phone screens so they didn't get scratched as much in their pocket or by their keys, and we've gotten that. But one of the things that comes as a consequence with is that our phone screens are now much more brittle. So when we drop them, they tend to shatter. Okay, so a lot of the time when we're making these properties, we need to remember that there's a trade-off. If we're going to increase one, we may alter something in another one. Okay, so in the case of iron, when we add in steel, remembering it's an interstitial alloy, so the carbon comes in and sits in between the metal ions, okay? As we increase the amount of hardness, we get harder and harder, okay? But we increase that brittleness. So we use small amounts of carbon for building materials, and then we increase it when we want something like chisels or where we want a sharp, hard edge, okay? But not necessarily that strength that we're looking for with construction. Okay, that's it. Okay, there's not much to alloying in terms of what we need to do, okay? And we don't need to know much about coating, especially at the moment. So really what we're after is understanding these key points from our study guide. And we should have done all those now. So if we have a look, the metallic bond being an electrostatic attraction between a positive and lattice of ions and delocalized electrons. We did that in video 1. Okay, the strength of the metallic bond depending on the charge of the ions and the radius of the metal ion. Again, we covered that in metal 1, so if you want to go over it again, go back and watch that. Alloys, well, we did those in this video. Explanation of electrical conductivity and malleability in metals. This was video 2. Explanation of the trends of melting points of metals. That goes back to the strength of the bond. Again, what we did in properties. Video 1 and video 2 covers that. And then the properties of alloys in terms of non-directional bonding. Have a go explaining that one yourself now that we've looked at the nature of an alloy. Can you explain in terms of the non-directional bonding within a lattice why they are harder? Okay, and why they may be a little bit less malleable. Okay, the other one is why they have lower electrical conductivity. We talked about that. See if you can write your own explanations for those, and we'll check them in class. Okay, and that's it. Until next time, make sure you check all the videos, and I'll see you in class.